All right. Yeah, in the first part of the last lecture, we talked about the desirable property of digital modulation, okay? And the most important two metrics here is the spectral efficiency and the energy efficiency, right? So those two would be more or less the last part of our class, right? So we'll focus a lot on the spectral efficiency. Basically, we need to focus on, to characterize the number of bits per second per hertz for a digital communication system, and also we're going to characterize, okay, so what is the relationship between this and the energy efficiency normally measured as the signal-to-noise ratio, okay? And there are some other desired property that we're going to talk about, but not focus on. For example, the synchronization capability, right? That's very important, but we're not going to talk much about it. And we're going to talk a lot on the PSD, right? Power spectral density, for example, today, right? So that's an extremely important metric that in our class. And also, there's some other desired property, including the error detection and the error correction capability and the transparency capability, right? So yeah, those will be the focus of some other kind of classes, right? And here in our class, we'll focus mostly on the modulation and demodulation for the digital signal, right? And you can see that the transmission, so how to convert it from the higher frequency component, the higher frequency part to a lower frequency part, that will be the same as the analog communication, right? You can use DSB-SC or DSB or FM or whatever to deal with that. As you can see, right? So most of the modulation technique are something that we have seen before, right? For example, we know ASK, amplitude shift keying, right? We know FSK, like BPSK, like BPSK, QPSK, right? All of those are kind of what we have seen before, right? But what we're going to focus on here is that, okay, let's say now we have a baseband signal, right? So what should we do? Okay, so how can we detect it's a 0 or 1, right? So those are our focus in this class, right? So for the pulse shaping, we're going to give you a few examples of pulse shaping, right? Because that will control your power spectral density, right? But how to design that optimally is not what we're going to focus, right? But yeah, due to the time limit. Okay, and the first type of modulation approach we talk about is called line encoding, right? So basically, that's a kind of technique that we use to transmit the baseband signal, okay? And normally what we do here is that, okay, if we mention line encoding, more or less we talk about binary, right? So basically what we do is that we convert a 0 to a waveform and 1 to another waveform, right? Normally they're very simple waveform like the rectangle waveform and so on. Okay, and in this class, particularly we focus on two classes of this kind of waveform. One is called a net return to 0 or NRZ. The other one is called return to 0 or RZ or RTZ. Right? Those are very simple waveform. Okay, so I didn't draw anything here, but so normally for NRZ, we have two cases. One is unipolar, the other one is bipolar. Right? So basically, what we mean here is that net return to 0 basically means that during one period of a symbol time, so because here we transmit 0 or 1, maybe we denote by TB, B means bit, right? So this can represent a 1, right? So basically, within a symbol period, we don't return to 0, right? It's all 1, right? And a 0 could mean simply nothing, right? So this could be means 0, right? So that's called a unipolar. If it's a bipolar, so basically means that 0, if we transmit something like this, like here is A, for example, here's it's minus A for the magnitude, and then, yeah, this is bipolar, right? And similarly for the, one disadvantage of the bipolar or unipolar here is that we may have synchronization issues, right? If, for example, if we transmit long string of 0 for unipolar, there's no way to tell it, right? Or if you transmit 1 all the time, there's no way to tell it, right? So it's not easy to synchronize. And the other thing for this one is what? Is the DC component, right? So if we transmit unipolar, not bipolar, so we're going to have a DC component here. So that may not be desirable because DC doesn't have any information, right? I want to avoid it. Okay, So one way to solve this synchronization problem is to use a Manchester NRZ. So basically, the Manchester NRZ means nothing, but we can transmit something like this within one period of symbol time. Let's say here's A, here's minus A. So that means a 1, and minus 1 is the negation of it. Right here, you can see this is changing all the time. Right then, there's a way to tell when the signal starts. Okay. Okay, and those are the non-return to zero code, and the return to zero code. Yeah, so for the return to zero code, it's just like this. So let's say for one period, so we just we have this. Okay, you return 0 at some point and then keep it 0 for the rest, right? That's return to 0. Okay, you can see an advantage of it is that you know it's maybe better for the synchronization, right? But if it's unipolar, then still have the DC component, right? If it's it's bipolar, then it's better, okay? But one problem here is that, okay, now the rectangle is narrower, then the bandwidth is bigger, right? That's a disadvantage of it. Okay, so yeah, that's the introduction for the RZ and RZ coding scheme. Okay, and then we're going to focus on how can we compute the power spectral density of line coding, okay? So the way to compute the power spectral density is as follows. So for this formula, Y is the received signal or the transmitted signal of the line coding, the data stream, and the A is our coded symbol. Okay. So for example, let's say if we use RZ, if it's NRZ like this, okay. So this basically means that if we transmit a 0, then we're gonna encode it. Sorry, if we transmit a 1. Okay, so we're gonna encode it into a 1. If we transmit a 0, then we're gonna encode it to this case, which is minus A or minus A, right? So that's basically, so those are the AK, right? So normally we denote this as UK. Okay, UK means the message, AK is the coded message, right? And then we can write down the transmit signal in this way. Okay, P is our shaping message, right? For example, if we include A here, and then we just write what? A 1 and a minus 1 here, right? Depends on where you put A is, the magnitude, the amplitude A is. Okay, so yeah, I think that is clear. And then, in order to compute the power spectral density here, basically, our idea is to use the autocorrelation function, right? As we said, right? If you recall the definition of power spectral densities, right? So it's kind of hard to compute it in the frequency domain because, when you define it within time limit, and then, we need to integral over the time limit, frequency limit, and then, we need to let that go to infinity. So it's kind of hard to compute. So, but what we can do is that we can compute that in the time domain for the autocorrelation function, and then do the Fourier transform, right? That's an easy, much more easier way to do it. So in order to do that, so we're gonna rewrite this as this formula, right? So basically, I write that as a convolution between the pulse shaping signal PT, right, and our transmitted signal, coded transmitted signal in this way, right? It's a delta train here, right, or impulse train, and if we denote this as x of t, this kind of input, right, and then we pass that with a filter denoted by PT, and then we can get y of t. Right? If we write that in this way, then we can show that the power spectral density of the output y equals to pf squared multiply the power spectral density of x. Okay, and this one is easily to know, right? Because the Fourier transform of this guy is just a sinc signal, right? No matter how how big is the width, but it's just a sinc signal, and square is a sinc square, right? It's easy. Okay, so now the hard thing is how to characterize this guy, right? So because x now is this, okay? We kind of didn't see that before, right? How can we characterize the autocorrelation function of this guy? Okay, so that's the focus of our class today. Okay, so today's our 30th lecture. And we're going to focus on line coding today. Okay, and in particular, we're going to focus on how can we compute the PSD. Okay, power spectral density. Right, so this is like, the Fourier transform of a random signal, right? So if signal is random, then, it's kind of difficult to see the property of that from just Fourier transform, right? So power spectral density can tell us, may give us a better view of what is really going on in the frequency domain, right? So this is what we compute all the time. Okay, so let's recall the system that we're studying. So basically, our input is a bunch of let's say here's -1. It's a bunch of impulses here, right? So that's our x of t, right? And so that is nothing but we sum it over k, and then t minus k tb, right? So that's basically our input. Let's say here is 0, then we have tb here, minus tb here. And then we input that into a filter, right, or our impulse, denoted by pt. And then the output is our y of t, right? And our y of t would be nothing but this. Right, so this is a system that we care about, and the goal is to compute the power spectral density of y. So that is equal to this guy. Right, so now our goal is to compute its Fourier transform of this guy, which is r x of tau, okay, the autocorrelation function. Okay. Yeah, let's see whether you still remember how to compute the autocorrelation function here. So basically, autocorrelation function is given by this. So we let capital T goes to infinity, then we normalize it over t. And right, this is the autocorrelation function of x of t. And let's see how we can compute it. Okay, so we sort of mentioned this a little bit, but didn't start compute it, right? So basically, in order to compute it, we have two cases to consider, right? So normally for this kind of weird function, or for any other kind of function, let's say if it's not a pulse train, right? If it's an impulse train, let's say if it's like a train of rectangle or whatever, or triangle, right? So this is the way that you should think about this, right? So basically, we're going to see, okay, so basically this is almost a convolution, right? The only difference between this and the convolution is that we don't need to do the flipping, right? But the idea is the same, right? Right, so basically, we better draw a picture of it, right? This is the first case, right? So if we draw a picture of this, let's say here's x of t, and then we draw another picture of x t minus tau, and see what are the product of these two is. Okay, so this is our x of t. Let's say here's our 0, here's 2 TB, 1 TB, 1 TB, 2 TB, and so on. Here's is a minus TB, right? And we're going to draw another one here, right? Let's say, for example, let's say here is xt minus tau. So the first case to consider is that, let's say, tau is not a multiples of TB, right? The first case, maybe let me write it here. The first case is when tau is not multiples of TB, right? That's an easy case to consider, right? So if the shifting is not multiples of TB, it'll be something like this, right? Right, that'll be t minus tau, xt minus tau, right? Then if we multiply this and that, yeah, what will be the product between the two? 0, right? That's easy. So great. So in this case, if this is 0, then the integral of that is 0, right? So we don't need to worry too much about it. So that will be 0, okay? So that is the case when tau is not multiples of TB, right? Very good. Okay, so what is not so easy is the other case, right? Yeah, let's see the other case. Second case is that if tau equals to multiples of TB, and then let's see what is going on here. See. So this is Rx of t, and the other one here is something like that, right? So let's assume that maybe for simplicity, we just draw the x minus 2 TB, right? So basically, we have something like this, right? But different here is the index here, right? If we shift it by 2 dB here, so here should be minus 2 TB, here's TB, here will be 0, here's minus 3 TB. And so on, right? Okay, so yeah, let's mark it. So here is A0, A1, A2, A3. Here's A minus 1, so this will be A minus 2, A minus 1, A0, and so on, right? So this is basically what we have, okay? And now if we use this, multiply that, and what do we got? Right, for example, if we use this one, multiply that, it's like A0 times A minus 2, right? Or, yeah, let me write, yes, A0, let's say for, use another color. I say for this two, right? So multiplication of this is what? A0 delta t multiply what? A minus 2 times delta t, right? Yeah, let's assume right here is that just 2 delta multiplied together, right? And then we have A naught times A minus 2, right? What does that equals to? Right, clearly it equals to A0, A minus 2, and then times what? Right, what is that? Anyone have seen this before? Can you see it? It's a delta times delta, right? So who have seen this before in your life? What is that? Yeah, it's really bad, right? It's artificial. Yeah, so actually, yeah, normally we don't have delta square, right? Because what's the meaning of it, right? And then, yeah, because of our mathematical model like this, then we have a delta square. How can we deal with that, right? So the easy solution is that we don't deal with that, right? We forget it, right? So what we do is that, okay, delta times delta, that's like equals delta. Does that make sense? Not really, right? Yeah, just ignore that, okay? We don't have this. Right, actually, as we said before, if you think it in a deeper way, right, I will give you the definition. So if you remember what's the definition of delta, it's like delta equals to infinity when it's at 0, and 0 otherwise. And then we have another condition, which is that the integral of delta is 1, right? But that's not a real definition. It's a definition that, we can sort of intuitively understand, right? The real definition is that we need to think about delta in a so-called distribution sense, right? So normally, actually, the sampling property is how we define delta really in math, right? But that is not our focus, right? So what we focus on is that, in order to really understand this, so you can take a look at the book, right? So if we don't do this kind of thing, we need to go to the harder way. So basically, we replace each of this guy by something that we can understand, right? For example, we replace each of this guy by a small rectangle, right, like this, and then multiply them together. And then let's say, for example, the width of the rectangle could be 1 over epsilon, and the height of that is epsilon. And then after our computation, we'll let epsilon go to infinity, and then we can have something that we like, which is kind of this, right? But you can go over the hard route, but I'm not going to do that in class since we don't have the time, and that is not extremely important. So basically, what we do is that we sort of like, delta times delta, we assume that equal to kind of delta, okay? Another way to think about it is that we can think delta t times delta t is like delta t multiplied times 0, right? And the delta 0 is kind of like a constant. We take that out of the integral, and then just use 1 delta to do the computation, right? And then we can have only 1 delta left. But this is not rigorous, okay? It is just a way to whatever. But that's not rigorous. It's not rigorous, okay? It's just a coincidence, okay? Okay, never mind. So now let's after doing this, I think it's kind of clear, right? So basically, we have some delta left, and then before it's kind of this, right? And we have every term is like, okay, a minus 1 times a1, a2 times a0, right? The difference between these two is all like 2 in this case, right? Which is basically this tau, okay? So basically, our conclusion is that now we can sort of using the autocorrelation function between these two, between the ak, and then we can characterize the autocorrelation function of that, okay? So basically, what we can do is that, so the output, the autocorrelation of x can be given by this. Change my notation to n here. Just bear me a little bit. We'll just use n here. Okay, and we'll have some whatever this coefficient here, and then we times that with a delta signal. Okay, so that's basically what we have. Now the question is, what Cn will be, right? What that value is. Okay, and as we said, right, Cn is some form of autocorrelation between the A's. Okay, so that's what we do. Okay, so now we need to be a little bit more careful here. So basically, because given this form, right, so you can see, okay, so this is kind of let's take a look at this. Okay, so basically we're gonna take a wide range of it with the length t and multiply them together, okay, and then do the integral, right? And when we do the integral, all this part will be given 0. Okay, the only thing that matters is like when we have this and that aligned together. Okay, so basically we can comfortably write this capital T as what? Let's say 1 over n times TB, right? Because it will be multiples of TB, right? And then this integral will become a summation. Okay, and then if it becomes a summation, then we can take, the capital N should not that N. If it's a summation, then we can basically, take this TB out and then keep this 1 over N here, and then we can have something very nice as an autocorrelation of the A case. Okay, so that's basically the idea. And by doing this, so basically what we can write is Rx tau as follows. It's equal to 1 over TB, right? As we said, we can take the TB out and keep the 1 over N inside. So then we can write that as this guy. And here the Rn is the autocorrelation of the A's, right? So as we said, we have 1 over N. We keep that inside. Let's see. Oh, actually, don't change the limit, right? The limit is still here, yeah. Okay, and then 1 over N, and then the summation range should be the length of N here, right? So I have AK times AK plus or minus N, doesn't matter really. And K equals to N over 2 plus 1 divided by, go over to this, right? Here, n has to be even number. But if you don't like it, it doesn't matter. You can just put a 2n here, and then you use, you know, the range will be like, you know, should be n minus 1, right? The range will be like 2n, n minus 1 to n, right? Doesn't matter. Okay, so here, just for simplicity, we just assume that, oh, no. Yeah, that's wrong. That should be minus n, right? Minus n plus 1, right? That's right. Okay, so we can write out the correlation as a function of this, right? So basically, yeah, those are just intuitive derivation, right? It's not rigorous. So the rigorous way to do that in this case is we need to replace it by a real waveform there, and then let epsilon goes infinity. Anyway, I think that is good enough. And so, yeah, so this guy, obviously, so that is the discrete time. Autocorrelation of AK. Right, and clearly here, if we can compute this, then we know that, and then we just do the Fourier transform. Okay, is that clear? Yeah, any questions? Okay, and you can easily show that you can do that on your own, so that is equals to, maybe I can write it here. So this will also equals to r minus n, so basically it means that it's an even function. Okay, so which kind of makes sense, right? It doesn't matter if it's you know, a naught times a minus 2, or you know, this how can I think about this? Yeah, because we're doing kind of this summation, right? So it doesn't matter if here is a minus n or plus n, right? Just, you know, we can. Yeah, if we can replace this plus n by minus n, then you can show that that's equal. So yeah, as long as we have all the terms here, I think we're okay, right? Okay, and another important property here we can see is that, so basically, if you look at this Rn carefully, so this is actually not a function of time, right? It's just a function of the difference n here, okay? So this Rn does not depend on time, okay? Depend on time. And it only depends on, because we have a summation here, so it only depends on statistical characterization. Or characteristics. Statistical characteristics of AK. Okay, we're going to explain what do we mean by this, right? The key part is that, so this n will go to infinity, right? If this n goes to infinity, right, then this summation will go to some expectation, okay? That's why we say so it depends on statistical characteristics of AK. Okay, so now let's assume that we know that, because now the only thing we need to compute is this guy, right? And computing that is very easy. It's not hard. We're going to give you some examples. But now let's assume that we know this already, and then how we can compute fxf, right? Because that's our goal, okay? So basically, we're going to compute the Fourier transform of this guy, right? That equals the Fourier transform of Rx tau, right? And that equals to the Fourier transform of this guy, right? It's 1 over TB. Then we have a summation Rn delta T minus NTB, right? And then, yeah, let's move the Fourier transform operation up to here, right? Because this is the only part dependent on T. Remember, the Fourier transformation, the Fourier transform is for T, right? The variable is for T, and then that's equal to 1 over TB sum over n Rn, and then we have our Fourier transform. Of this guy. Okay, great. And then so the Fourier transform of delta, what's that? That would be a phase shift, right? It will be a complex exponential minus j and let's see what I use, f, 2 pi f and TB, right? Yeah, let me reorganize it. So 2 pi f and TB, right? So that's basically the Fourier transform of SXF. Okay, and we're done. Right? That makes sense? Is that clear? XF will basically equals to that, and then we just need to compute this guy to know exactly what SXF is. Okay. All right. Yeah, let's see. So in practice, we need to compute it under a sum of assumptions, as you will see later. So normally, when we finish computing it, like this, right? Let's say if Rn, let's say it's not a function of n, okay, if it's a constant, then we can just shift it and move it out, and then we're going to have a summation of a bunch of delta, okay? And then summation of a bunch of delta, then we can have another form, Fourier transform for that, right? A number of delta is still a sum of number of delta in frequency domain, right? We may have something, look different compared to this, Okay. Okay, and another comment for that is that we know Rn is an even function, right? Since it's an even function, and then we can simplify that a little bit to get rid of the complex exponential, right? Because it's an even function, right? So basically, that all equals to this. We take this 0 term out, and then we can combine the rest. Right, just use the Euler formula, and we can arrive here. Okay, so this is another way to compute it. Okay, so now the last question is how to compute Rn, right? So yeah, we still have it have it here, right? Let's look at this. So the last question is how to compute this. Okay, let's see how we can compute that. So yeah, basically, because we have a summation there, right? So basically, what we're going to use is the law of large numbers, okay? And also we assume the so-called system is ergodic, right? So who heard about ergodic system? No? Okay. So basically, we're going to use something like this. It's very nice. So here, we're going to use mean ergodic property. Okay, we say if a system is ergodic, so basically, it basically means that the time average will converge to ensemble average. Right? So what does that mean? So basically it means that, let's say, our system so if you want to compute that, so this is like our time average. Whatever, sum over n. Okay, so this time average will basically equal to the expectation of AK multiply K plus n. Right, does that make sense? Or, so another thing is that, let's say, this guy, that will converge to expectation of AK. Right, that's basically means ergodic system, right? So this side is the time average, and the expectation is the ensemble average. That clear? Right? It seems a natural thing to do, but it's not natural at all, right? Because so here is average over time, but so the variable here is time, but here the average is over all the possibilities, right? So this is a common assumption in wire system, right? So normally the time average will equal to the ensemble average. And this is what we do in practice, right? So how to estimate the expectation of something, right? So what we do is that we take a sequence of samples and then do the average of them, right? If that is not true, then how can we estimate the ensemble? That clear? Okay. So if we have this property, then it's good, right? So the only thing we need to know is what is the statistical property of this AK. Okay. So if we know the distribution of AK, then we're fine. Okay, and this is basically what we're going to assume here. Okay. And so basically what we're going to do is that we're going to assume UK. Remember, UK is the real information, and AK is a mapping of this information. Okay, so we assume that UK is an IID. Okay, so IID means the following. So the first I means independent. And second I means identically. And D basically means distributed. So independent, identically distributed random variable, right? What does it mean is that, okay, so for each K, the distribution of that is the same. And then for each K, they are independent, right? Statistically independent. Okay, and so because that's the original information, right? So normally what we assume that is IID, and because remember it's 0 and 1, right? It's binary. We assume that follow a Bernoulli distribution. Bernoulli distribution with half parameter. Okay, so this basically means that the probability that UK equals to 1 equals the probability that UK equals to 0, and both of them equals to half. Okay, yeah, that is what we assume all the time, and it's very valid distribution, right? Because as we said, for the source information, not 0 and 1s, so we can apply some kind of compression approach, right? So after compression, so this is normally what we get. Okay, that's a very valid assumption. Okay, and yeah, we know this, and also we need to make sure that UK and UL for any K and L as long. So this is meaning for this notation meaning for all. Okay, for all K and L, of course, K not equal to L, so those are independent. right? This independent basically means it's stochastically independent, right? So this basically means that the joint distribution of UK and UL basically equals to the distribution of UK times the distribution of UL, right? So this means statistically independent, right? Doesn't mean they are logically independent, right? They can be dependent logically, but statistically they are independent. Is that clear? Okay, great. And with all of this information, so we're ready to compute this. So first of all, we're going to map UK to AK, right? So this map is the deterministic mapping, right? So given UK, you know AK. Given AK, you know UK, okay? And in this way, so now let's, because AK will determine what kind of PT, waveform, you're going to get, right? So let's see the most simple case, right? So which is bipolar NRZ. Okay, for the bipolar NRZ, so basically what we get is that when UK is 1, then we have this form, A here, T, and when UK is 0, and then this is what we got. Minus A here, right? So basically in this case, we can see when UK is 1, and then AK is also 1. And when UK is minus 1, then AK is, sorry, when UK is 0, AK is minus 1. Okay? Is that clear? And of course, you know, now PT is nothing but this in our case. Okay, and so in this case, because we have this assumption, right? So they are Bernoulli, UKs are Bernoulli distribution. So then we can get the probability of AK is 1 or equals to the probability of AK is minus 1 equals to half, and they are independent, right? So in this way, we could compute all the statistical metrics of it, right? The expectation of AK is what? Right, you just compute using the definition, right? So basically, we have 1 multiplied the probability of 1, which is half, and then another value of it, just minus 1, and times the probability of it, that'll be 0. Okay? Yeah, do you still remember how to compute expectation? Right, the value multiplied the probability, and then similarly, we could compute AK squared, right? So that's basically 1 multiply half, 1 squared multiply half plus minus 1 squared multiply half. That is what? 1, right? Okay. And remember, so our goal is basically to compute that, right? So basically, now we know when n is 0, right? And we compute that, and we need to compute when n is not 0, right? So when n is not 0, let's see what does that equals to. So the expectation of AK and AK, or we just write L here, when K and L are not equal, right? Yeah, because they are independent, you have to consider the case where K not equals to L, right? When K is not equal to L, so they are independent, then we can break it, right? So that's the expectation of AK times expectation of AL. And we compute it here that each expectation will be equal to 0, right? And then that'll be 0, okay? So, great. Okay, and because of the ergodicity, right, we assume so this equation holds. Okay, so now we could evaluate this is Rn, right? So we can evaluate Rn. Okay, so actually Rn is insanely simple, right, in this case. So basically, let's see. So when n equal to 0, when for R0, so that is basically this guy, right? So that is 1. And for Rn, that n is not 0. So what does that equals to? Yeah, that'll be this guy, right? 0, and that's it. Okay, so that is very simple. And now let's compute what is xf. Yeah, I didn't remove it here, right? So this is xf, as xf, right? And we can see that. So this is summation over n, and this is Rn, right? So in our case, only n is 0, we have something. Otherwise, it's 0. Then we don't have the summation anymore. We just have R0 left, right? So in this case, let me write it here. Let's see. Sx of f equals to R0 over TB, right? And what's the left? Yeah, whatever left here is that if we put n equal to 0, so this guy will be gone, right? It'll be a 1, right? And that'll be it. Right, this will be Sx of f, right? The PSD of x. In our case, okay, then we could compute Sy f equals to Pf squared times Xs f, right? And since we have that, and by the way, so we know R0 is just 1, right? Just 1 there, so that is 1 over TB. Okay, and this guy would be just equal to Pf squared over TB. Okay, now the only thing we need to know is what is a Pf here, right? And we know the Pf is a square wave form, look like this. This is PT, right? With magnitude of A, okay? And then because we square it, right? If we will compute the Fourier transform, so we have a time shift, then we have a phase shift in the frequency domain, right? Consider if it's this case, right? But we don't care about it because we compute the square of it, right? Absolute value square, not just square, right? Absolute value square of it. We can ignore the phase shift, so this will be just a sinc square, right? We have A square, TB square, because we need to put a TB in front, and the sinc pi f TB square. Okay, that'll be it. All right, and then we can plug that in, right? So Sy f would be nothing but we divide this by TB here only, right? So it should be A squared TB sinc pi f TB. All right. Okay, and this is our PSD, okay? And this is the procedure of the computation, right? We compute Rn first, and then plug into our formula, and then get the final result, okay? And yeah, let's take a look at what it looks like in the frequency domain. So it's a sinc square signal, right? So basically, the PSD looks like this, right? It's a sinc square, still like a sinc, but everything is positive. Right, here's 0, here's 1 over TB, 2 over TB, and so on. And here the magnitude is A squared TB. And yeah, in the frequency domain, it looks like that. Okay, and I have many examples on other kind of unipolar NRZ and bipolar and unipolar RZ, bipolar RZ. They're this procedure follow exactly the same way here, right? So you can, I think I'm going to upload all the nodes online. You can take a look on your own. I think I have all the details here. The computation is pretty clear. So I don't have time to go over all of them. So yeah, this is, and we're done for this. Okay, and we're going to do something else in the next lecture. Okay, starting a new topic. Okay, I think that'll be it for today. Yeah, thanks.